In this video, we're looking at section 5.5, integration by substitution. All right, now this technique, what we're doing here is actually the reverse of section 3.4. All right, we need this integration by substitution. This is needed. We need to do this when we have an inside function other than x. Okay, so what section 5.5 really is the reversing, we're reversing or doing the opposite of what we did in section 3.4, the chain rule. Okay, now 5.1 was actually the reverse of the basic derivatives that we learned in section 3.2. Okay. All right, so like if I did the derivative of y equals the quantity 3x squared plus 5 to the 7th, we know how to do that. We bring the exponent down, we subtract 1 and get a 6, we multiply by the derivative of the inside function, and we wind up with 42x 3x squared plus 5, raised to the 6th power. That would be the derivative. That would be dy dx. All right, at some point, we're going to want to try to integrate something like that. So at some point, we're going to be thinking about how this is dy dx. We're going to have, so that means dy would have been 42x 3x squared plus 5 raised to the 6th with a dx over on the right. And then what we're doing in this section is we're going to be integrating things like this and trying to figure out that this right here would have come from a function like that. We're going to have to try to undo that and understand where it came from. So we're building towards being able to do that type of thing. Okay? There's going to be one thing you're going to like. There's going to be a set process you could use that virtually works, every single time. But you also could use a shortcut, observing the patterns, that'll work in some cases when the constants are really easy to figure out. All right, but let's go ahead and just get started on this. All right, so we remember how with the chain rule, whenever you did the derivative, you had to remember to tack on the derivative of that inside part. That's what we're trying to reverse now. Okay. So we know doing the derivative of a power function like this, the general power rule would have been bring the exponent down, subtract 1 from the exponent, and then do the derivative of u, and that was the u prime right there. All right, well, we were working on reversing the power rule in the previous section already. Okay? So we kind of knew that idea of we need to add 1 to the exponent and then divide by that. Okay? So that's going to come into play here. All right, they're reminding us that if there's a multiple, just a number out in front, that you can just like with derivatives, you were able to just carry it along. Same thing's true when you're integrating. If you have just a constant there, you can just carry it along. Okay. All right, so as we're looking at this, okay, this g prime d of x right here, this whole part right here, that right there is the du. Okay. And then let me think where I want to write that. Yeah, I'll just squeeze it in right here. So on this one, we could have thought of this more like we're integrating f of u, where u is some function of x, like 3x squared plus 1. Then all of that g prime of x dx is your du. Okay? And what we'd wind up with is f of u plus c. All right, so if we wanted to try to integrate this problem right here, let's just think about this. Then what we would notice, or hopefully notice, is that the inside function, 3x squared plus 7, its derivative is right here. That's the 6x. That's where that would have come from. So we might be able to do this one by just thinking, kind of like we did in section 5.1, and thinking about how the exponent of 6 would have had to start out being a 7, but I want that 7 to go away when it gets brought down in front, so I'm going to put a 1/7, and that is going to turn out to be it, because after that 7 comes down, like when I'm checking it, after that 7 comes down, this is the check, then I'm going to subtract 1. I'm going to multiply by the inside derivative of the inside function, which is 6x. Those cancel, and I get right here what I started with. So it checks. Now here in 5.5, we're back to indefinite integrals. We do not have limits of integration on our integration symbol. Remember the plus c? And that's just because we could have had any constant added there at the end, and the derivative of that would have still turned out to be the quantity 3x squared plus 7 to the 6 times 6x. All right? So pattern recognition, just that idea, works really good when what you're trying to do is perfect, when they gave you the derivative of the inside function. So what I wanted to look at here was how to think about this, how to look at it and try to find how to see what's going on. What I like to do is I like to look for what's been raised to a power, what's under a radical. Okay, that's your inside function. Now, do you notice how that 2x right there is the derivative of x squared plus 1? That means that would be a great candidate for just using pattern recognition. The u, we're trying to turn them into, we're trying to think about identifying the f of u and the du. The u, that would have been the x squared plus 1. The derivative of that would have wound up being 2x dx. Okay. So let me say that a little bit better. If you notice that you have the derivative of that inside function right there, then that means you could make a substitution on this. And you could think about this as just the integral of something squared, and then that something, that u that you had right there, oops, let me not do the derivative yet. Won't erase. Okay, so that u on this one would have been the x squared plus 1, and the derivative of u with respect to x would have been 2x. So I could move that dx over, and du would have turned out to be 2x dx. So that means that 2x dx could be replaced with du. And then that's an easy thing to integrate. That's kind of the idea of what we're going to do in a moment. But right now, all we're doing is we're looking at, for this one, I want you to start looking to see if you can recognize, here's your inside function, the x to the third plus 1. Do you see where that 3x squared came from? The derivative of x to the third plus 1, wouldn't that be 3x squared? So it came from that inside function. So we're going to change this one into the integral of u to the 1/2 power for the square root of x, and then that 3x squared together with that dx, that's going to be the du. Okay. All right, now when you have one like this, especially sines and cosines, they can be kind of interesting. This one you might want to think about as being cosine x with the sine brought up to the top. And then when you're looking at that, think about the sine x as what's being raised to a power. So that's like your inside function. And then the derivative of that would turn out to be cosine x. But we're going to have this little dx on it, you'll see, because we're going to be calling this u. And so du dx would equal cosine x, and that dx will go over to the side. So du will be cosine x dx. All right, so first we weren't really going to be integrating on all these in the table. We're just getting the idea behind it. All right, I want to do these two here by trying to use pattern recognition, since that x squared minus 9 kind of tells me where this 2x would have come from. So if I were trying to do this one without any change of variables and all that we're going to do later, I might just think about how this would be the inside function. And if I want the exponent to be a 3, it had to come from a 4. But that 4 would have gotten brought down, and I need it to cancel out. So I'm going to put a 1/4 out in front to make that happen. But then I would need the derivative of the inside part, which would be where that 2x came from. So this is actually it, and I'm done. Okay. Now, remember on these, especially if you're going to do it using pattern recognition, that your check would be coming in and doing the derivative with respect to x. So your check would be coming in and seeing, okay, I'd bring the 4 down, I'd subtract 1, okay, I'd do the derivative of the inside. The derivative of c would have been 0 because it's a constant, and then I would have gotten the x squared. I would have gotten what I needed right here. I would have gotten the x squared minus 9 to the third with that 2x. Okay. Okay, got one more I want to do, and then I'll do a second video on this. All right, so here I'm going to do a rewrite to see that 3 minus 4x squared as a power function, as something raised to the 1/3 power. Then I've got this negative 8x dx. Now that little dx, that's just telling me that I'm integrating with respect to x. Okay. So on this one, I like what I see because that right there is the derivative of the inside function. Just like this right here was the derivative of the inside function. Those are the ones that are especially nice to do just using pattern recognition. So feel free to do that if you're comfortable with that. So I'm now starting to do the integration of this. I'm starting to undo this. So I'm going to have 3 minus 4x squared in parentheses. For me to wind up with a 1/3, I needed to have had a 4/3. But that 4/3 would have come down in front when I do the derivative. So put a 3/4, the reciprocal of that, so it cancels out. Okay? And now notice that the negative 8x would have come from the derivative of the inside function. So that should be my answer. All I got to do is get it back to radicals. And that's a positive exponent, so that radical is not going to go to the denominator. It's going to stay on top. Still going to have the 3 minus 4x squared underneath. Okay. But that 4 means I either need to put parentheses around this to the 4th or around the whole radical. I could have put them there, or I could have done that. That works good when you're evaluating later. Okay. Now I still have a 4. I can either put the 3/4 out in front or put the whole thing over 4. And then don't forget that plus c. And then you can check this. And when you do, you should, if you did the derivative of this as your check, you should wind up with that right there when you're finished.